welcome to a new episode of Forecasting Economics, where I cover applied time series analysis and forecasting tutorials. In today's episode, we are going to explore vector autoregressions using R. My name is Juan D'Amico and I'm an economist. If you enjoy hands-on application using real-world economic data, I invite you to subscribe to the channel. Feel free to leave a comment with your thoughts and don't forget to like and share the video. Let's get started. Let's quickly review what the paper is about. Stock and Watson in 2001 assessed the VAR framework that was introduced by Sims in 1980. At the time, that paper offered a new and a promising approach to macroeconomic modeling. In the moment, what they were doing is estimating very complex models that relied in many structural equations. So this article is going to review how well the VARs perform across four tasks. They are data description, forecasting, structural inference, and policy analysis. To do so, what they do is they estimate a three-variable system that consisted of inflation, unemployment, and the federal fund rate. By the end of this tutorial, you will know how to estimate a VAR model, how to select the lag length, how to compute impulse response functions, variance decomposition, conduct a Granger causality test, and the most important part is how to produce forecasts using VAR models. Alright, let's break down the mathematical representation of a VAR model. At high level, a VAR treats all variables as endogenous, meaning that each variable is explained by its own past values and the past values of all the other variables in the system. In our case, we're working with three variables. Remember, they are inflation, unemployment, and the federal funds rates. And we are using four lags following Stock and Watson. You can see the notation for the lags in this section of the equation. Now, if you look at these equations, each one corresponds to one variable. For example, the first equation explains inflation today as a function of past inflation, past unemployment, and past interest rates. The same idea applies to the other equations. Each variable depends on the full history of the system. So instead of modeling each series in a separate way, we are modeling them jointly, which allow us to capture the dynamic interaction across the variable. Now, to simplify things, what we can do is we can write this in a compact matrix form. The first vector contains the dependent variables. In this vector, we have the constants. The main matrix contains all the coefficient values. And here we have the residuals. One important point is that it's a reduced form VAR, meaning that the error terms are combinations of underlying structural shocks. To interpret those shocks economically, we're going to need an additional identification step, which I'm going to cover in the next slide, because I'm going to provide you more information when we talk about impulse response functions. Now we move to R and estimate our VAR model. I already have the data loaded in my environment. In a previous tutorial, I showed you how to use the Fred API key to automate data collection, so you don't need to download Excel files constantly. But if you prefer, what you can do is you can download the dataset directly from the link in the video description. To estimate the VAR, the first thing that we're going to do is to organize the variables into a matrix. I've selected the variables that we're going to use, that are inflation, unemployment rate, and the federal funds rates. Next thing is to use the VAR command. You're going to type VAR, and the arguments that you're going to include are our matrix that contains our data, the number of lags that we want to include, and a constant term. Finally, what we can do is we can print the results using the summary command. I'm going to select it all, and we're going to run the script. Here we can see the output that is showing the coefficients for each of the equations that we have specified in our model, along with the standard diagnostics. Now, something you can do if you want to learn more about the available options with the VAR command, you can type in the help section, VAR. You are going to find all the different arguments that you can include in the VAR specification. Before estimating the model, it's always a good practice to check how many lags we should include. In our case, we have used 4 lags to follow Stock and Watson. However, we can also rely on statistical criteria to guide this choice. Here, I'm going to use the VAR select command, and I'm going to allow the software to evaluate up to 8 lags. I'm also going to include a constant term. I'm going to run the script, and here we get the output. Right away, what you can see is the different information criterions. We have the AIC, which is the Akaike, HQ, which is Han and Queen. We have SC, which stands for the Schwartz criterion, and we also have FPE, which stands for final prediction error. Each of these criteria balances model fit and complexity, but they often tend to suggest different lag lengths. As we can see, one is suggesting 8, another one 3, another one 2, and another one 8. There's no single correct number of lags. A common rule of thumb would be to look for consistency across criterions. That is, if we have many criteria that are suggesting a specific number of lags, we should be using that type of specification. The other thing that we can do is that we can choose a specification that can make economic sense or statistical sense. In the case of the authors, they have used 4 lags because the data is quarterly and most likely they try to allow for 4 lags of dynamics in the system. It's important to note that the number of lags can significantly affect the results, especially the dynamics that we can observe when we compute impulse response functions and when we produce forecasts. So while we are going to follow the paper and use 4 lags, this step always helps us to understand the sensitivity of our model to different lag choices. Another thing that you can do if you want to get more information is you can copy the command VAR select and you're going to paste it into the help section. In here, you're going to get a summary and a description of all the different criterions and how we can use the different specifications and details of how we can compute each of these criterions. Now let's move to impulse response functions. An impulse response function traces the dynamic effect of a one-time shock to one variable on all the variables in the system over time. To build some intuition, suppose there is a shock to inflation today. We can then ask, how does unemployment respond? And how does the central bank react through the federal funds rate? So an impulse response function allows us to track these responses over a given horizon, for example, in the next 24 quarters. Now I'm going to go into R and implement the impulse responses. To compute the impulse responses, I'm going to use the IRF function. The first thing that I'm going to do is to create an object for each of the variables in my model. The next thing is going to be use the IRF command, and the first argument is going to specify the model that we have estimated. Remember, I'm going to show you up here that the model, the VAR model, we estimated with the VAR command. We called it VAR model. So that's why we are using this argument in here. The next thing we need to define in the impulse response functions is which variable is the impulse. The next thing is how many periods ahead we want to compute the impulse responses. I'm also going to apply orthogonalization, which is going to allow us to interpret the shock as an independent innovation. This relies on a recursive identification, which means that the ordering of the variables matters. I'm going to discuss this a bit more in the next section, where I'm going to cover identification strategy, and you are going to get a better idea of what I mean by recursive ordering. The next thing that I'm specifying here is the argument boot, that is for bootstraps. I'm going to quantify an uncertainty using bootstrap method with 500 replications. Also, I'm going to compute the confidence intervals with a 68% band. So these are all the arguments that we have in our IRF command. Finally, what we can do is we can plot these impulse response functions just using the plot argument. Now, as I have mentioned before, I always recommend that you copy this command and you paste it in the help section, because you're going to get a lot of information about all the different arguments that you can include in your IRF specification. You can get details, you can get a lot more information that is going to complement your knowledge. Now let's grab all this and let's run the script. Once it's done with the computation of the impulse response functions, it's going to plot them in the plot section. In this case, we can see the orthogonal impulse response from the federal fund rates. Before discussing a bit more impulse response functions, what we need to address first is an important issue, which is identification. So far, what we have done is we have estimated a reduced form VAR, that is what we have seen in the mathematical representation of the model, where the residuals are combinations of underlying structural shocks. What this means is that we cannot directly interpret the shocks economically. To do that, what we need to do is to implement an identification strategy. In this tutorial, what we're going to do then is we're going to use a recursive identification, which is implemented through the Cholesky decomposition. This approach imposes an ordering on the variables, which is going to determine how the shocks are going to propagate contemporaneously. In our case, we're going to follow Stock and Watson, the paper that we're replicating, where they select first inflation, then we have unemployment, and then we have the interest rate. Now, the question is how we are going to order the variables. What you can do is use some economic theory to be able to establish a causal ordering between these variables. What we can think of between inflation and unemployment is the Phillips curve relationship, and when we have the federal funds rate at the end that is allowed to respond to inflation and is allowed to respond to unemployment shocks, we can think of as the reaction function of the policymaker. When anytime they see significant changes in inflation or unemployment, they are going to modify the interest rate. The fact that inflation doesn't respond in the short run to unemployment or the federal fund rate has to do with price stickiness and nominal rigidities. What we can think of is that it's always going to take a lot of time for prices to respond to changes in the interest rate. Also, the same is going to happen with unemployment. We can see that unemployment is not going to respond to changes in the interest rate in the short run. The reason for this is because the structure of the markets are rigid. They are not flexible in the short run. It's not that we can modify the federal rate and then the markets are going to react immediately. Now, the ordering is crucial because it directly affects the impulse response functions. So when we compute the IRF and we use the orthogonalization option, we are implicitly using this recursive structure, and changing the order of the variables is going to lead to different results. I have talked to you about impulse response functions. I have talked about the identification strategy and how we are going to use the recursive ordering. But the next question that should come to your mind is, what is the magnitude of the shock that we are applying? Anytime that we shock one of the variables in the system, in what units is the shock? By default, the shocks are measured in standard deviations of the residuals. This can be convenient statistically, but it's not very intuitive from an economic perspective. To illustrate and give you an example, let's plot the impulse response function for the unemployment rate. We can see that the line, the row that corresponds to unemployment is the middle one, and the shock would be somewhere around 0.25. You can see here, it's around 0.25 percentage points. All right, so anywhere between 0.2 and 0.25 percentage points is a standard deviation of the residuals. Okay, so how can we get a more accurate magnitude of the shock? What we are going to do to answer that question is we're going to compute the standard deviation of the shocks directly from the VAR. These are going to come from the covariance matrix of the residuals. I have here already the command. We're going to run the script, and all we are doing is obtaining from the VAR model the covariance. And we are extracting, of course, the square root of the variance, which is the standard deviation. We can see here the values for the standard deviations. That's the object that we have created. And we have that the unemployment rate, the magnitude of the shock, is 0.23 percentage points. So a one standard deviation shock to unemployment corresponds to about a 0.23 percentage point increase in the unemployment rate. The same happens with inflation, which is around 0.97, you can see here. And finally, the Fed fund rate, which is 0.89. This is going to help us understand a bit better the impulse response functions, but what we would like to do instead is to work with different magnitudes, and in this case I would like to work with a 1 unit change. Instead of working with all different units of measure, let's standardize these and let's make them all 1 percentage point. So instead of being 0.96, 0.23, 0.89, let's normalize the impulse response functions and let's make that all the shocks are a 1 percentage point. So I'm going to show you now in the next section how we're going to normalize the impulse response function. In this section, I'm going to show you how you can plot all the impulse response functions in the same screen as the authors do. And also, I'm going to show you how you can normalize the shocks. With this first command, what we're doing is displaying all the impulse response functions in a grid, which is 3 by 3. And here, what we are doing is dividing the impulse responses by the standard deviation of the shock. Remember that we have computed the standard deviation of the shocks in the previous section. Now I'm going to select all of these. I'm going to execute this command. And I'm going to hit enter to see the plot. Now we can see all the impulse response functions in the same screen, and you can tell that the shocks have been normalized. Another thing we can do is to replicate the figure that was presented by Stock and Watson. In this case, I'm not going to go through the full code because it's very lengthy, but if you're interested, you can access the full replication file in the description of the video. Let's run the script. You can see that this graph looks exactly as the one that was reported by the authors in the original paper. Now let's interpret the impulse response functions. First, what you should notice is that the main diagonal shows each variable response to its own shock. Also remember that we have normalized the shocks, so all of them start at 1 percentage point. The way you are going to read this figure is by rows. The first row is going to show all the responses to an inflation shock. The second row is going to show all the responses to an employment shock, and the third row is going to show all the responses to an interest rate shock. Let's analyze the main results. Starting with an inflation shock, we can see that inflation has a positive effect on unemployment, and at the same time, the policymaker is going to respond by increasing the interest rate. This is consistent with a tightening of the monetary policy. Next, we can look at the shock to unemployment, and we can see that higher unemployment leads to a lower inflation. This is consistent with the Phillips-Core relationship. In response, what we can see is that the central bank is going to reduce the interest rate to stimulate the economy. Finally, we can look at the monetary policy shock. Here, what we find is a well-known puzzle in the VAR literature, which is that a contractionary monetary shock appears to increase inflation in the short run. This is not what we would expect theoretically. The issue is common when we are working with VAR models, and that's because we are working with realized data. Sims in a paper suggested using additional variables, for example, including commodity prices to act as an information variable and try to mitigate puzzling dynamics. However, this doesn't really work properly. Anytime that we're working with realized data, we are going to encounter identification problems with the monetary policy shock. Now, in more recent approaches, what we see in the literature is that they are relying on methods like the local projection that was introduced by Jourdain in 2005, and what they do is normally identify monetary shocks using a narrative approach such as that one that was proposed by Romer and Romer. We can definitely explore local projection methods in another tutorial, so if that is something that you would like to see in the next video, please let me know in the comments what you would like to see, and I'm going to work in a tutorial where I cover projection method and also the Romer and Romer shocks. Next, we can look at the forecast error variance decomposition, which is going to tell us how much of the variability in each variable can be attributed to each of the shocks. In other words, we can answer a question like, what fraction of inflation changes is explained by monetary policy shocks at different horizons? So the way we're going to compute the variance decomposition is by using the command forecast error variance decomposition. Let me copy the command and I'm going to show you in the help section what the syntax looks like. Here we get all the information about the forecast error variance decomposition with all the details and the calculations. And the syntax is very simple. The first argument is what's our VAR object, which we had called VAR model. And then we have to tell how many steps ahead we want to compute the variance decomposition. Finally, what I have done here is print the results at different horizons as the author have done. They report the variance decomposition at 1 quarter ahead, 4 quarters, 8 quarters, and 12 quarters. I'm going to run the command, and here we get, on the first hand side, we get the plots, where it's going to show how much each variable contributes to explaining the forecast errors of the variance. We can see inflation, for example, is the main contributor in the changes in inflation. We can see for the Fed funds that unemployment has a significant effect on the way the Fed are going to change the policy rate. Let's look at the table. Remember, by construction in the short run, inflation is not going to respond to changes in the unemployment or the federal fund rates. That was done by the recursive ordering. But then we can see that after 12 quarters, this is item number 4, we can see that unemployment can explain up to 12% of the changes in inflation. Let's look now at the unemployment rate, and we can see that after 12 quarters, inflation can explain up to 23.4% of changes in unemployment. On the other hand side, the federal funds can explain up to around 18.6% of the changes in unemployment rate. Finally, we can look at changes in the Fed rate. We see that inflation explains up to about 18%, and we see that the unemployment rate is the main contributor and it explains up to 56.4% of the changes in the fund rate. That's something we can see visually here. The gray part, we can see the evolution over the different horizons, and unemployment is one of the main factors for changes in the Fed fund rate in this model. Next, I would like to conduct the Granger causality test, which is going to ask whether the lag values of one variable help predict another variable in the model. The command for this is Granger causality. I'm going to copy, I'm going to go into the help section, and we can get more information about the description, the usage, and the arguments of the Granger causality test. It's very simple. All you need to include in here is the VAR object and the test we are using, which is the F test. I'm going to print all these results in a table and we can look at the results. In this table, we're going to find the p-values for the Granger causality test. In the columns, we have the variables being predicted, and in the rows, we have the variables we are testing as a possible cause. So, if the p-value is bigger than 0.05, we have that there is no evidence of causality. If the p-value is smaller than 0.05, Granger causality exists. So let's take a look then at the first example. We have that inflation does not Granger cause unemployment, but there exists Granger causality with interest rates. In the second row, we can see that the unemployment helps to predict inflation and it helps to predict the interest rate. Finally, the interest rate doesn't help to predict changes in inflation, but it helps to predict changes in unemployment. The last thing I would like to show you in this tutorial is how to produce a forecast with a VAR model. In this case, we're going to do an in-sample forecast because then we can compare with actual values. What we are doing in this particular line, we are splitting the sample. I'm going to split all the data set up to 1996, and then we have an out-of-sample forecast period, which is between 1996 and the year 2000. The next thing we're going to do is we are going to define our variables for the VAR model, and we are going to estimate again our VAR model, but now we're going to estimate it in the in-sample period. So we're going to estimate the VAR model up to the year 1996. The next thing that I'm going to do is to produce the forecasts using the predict command, and I'm going to produce a forecast of 16 periods ahead using a confidence interval of 95%. Finally, with this line, I'm going to plot the forecasts. So let's select the whole script here and let's run. We can see now in the screen the plot of the forecasts. We can see that the model predicts inflation to go up, the unemployment rate to slightly decrease, and the federal fund rate to be somewhat stable around the 5% line. The last thing I would like to do in this video is to show you how the forecast compares to the actual data. I'm going to select all the script because I have put together a very nice graph. So let's run this portion of the script and we're going to be able to compare whether our model has done a good job predicting inflation, unemployment, and the federal funds rate. Let's run the script. And here we get the graph of the forecast with the actual values. Let's go quickly through these forecasts. In blue, we have the predicted values, and in black, we have the actual values. Remember that this is an in-sample forecast, which is great because we have actual values and we can see how well our model has done at predicting future values. If we look at inflation, our model was predicting that inflation would go up, but in reality what we saw is that inflation didn't go up significantly. Indeed, it went down in the short run and then it stabilized somewhere around the 2% line. We see unemployment here. Unemployment, our model has predicted properly that it would decrease, but it didn't decrease with the same magnitude that it actually did. If we look at the federal fund rate, we can see that our forecast was quite decent. It did a good job trying to predict how stable the federal fund rate would be in the coming quarters. So this is the in-sample forecast for our VAR model. I hope that you found this video useful. This is going to be all the content for today. Please leave a comment in the video. I would like to know your thoughts. I would like to hear what you would like to see next. I invite you also to download the dataset, to replicate the material, and remember that for those interested, you can buy the guide and you can buy the replication file, so you will be able to get to all the same results that I have shown you in this tutorial. I'm going to see you in the next video.